Now let's look at the proximity-based techniques for outlier detection. There are two broad categories of proximity-based techniques. One is that it is a distance-based, so an object is considered an outlier if within near distance there is no other point. And the other technique that is used is a density based outlier detection. So it is within a range or around this object, the density of other objects is low, then it is considered as an outlier. So here again the logic is pretty much same. So here we are looking at a significant deviation either with respect to distance or density before declaring that a data object is an outlier. So first look at distance based outlier detection. So we go with the definition. So we say that we start with a user specified threshold. To start with, let's say R is a user specified threshold, and we are looking at the number of objects in the R neighborhood of O. And then we will also use the pi as a fraction of threshold, saying that let's say 1% the object. So if it says that not even 1% objects are available within this distance, within the R neighborhood, then we may consider the object O as an outlier. So it comes to like this. So to what we are saying is that it can be expressed in terms of a distance based outlier with two parameters, which is R and pi. With a definition such as this, we are looking at the count of objects such that the distance from O, so we are finding for all O prime, so for the distance with O is less than R, and we are dividing it by the total count of the data objects, and we are seeing that if it is lower than this fraction threshold, then we consider the O as an outlier. So the other way we may be able to do is to use a kth nearest neighbor. So for each object, we can find that instead of what is the nearest point, that we find out the kth nearest point. We know that less than k objects within that distance. Then we can say that if that is representing that the kth neighborhood is equivalent to essentially R, if we say that the kth neighborhood is at least R distance away, so it is a alternative way of expressing it. So then we are saying that that k is representing obviously the same fraction as this pi multiplied by the total count of the objects in the domain. So we may have a smooth efficient algorithm for doing it for distance based outlier detection. So here what we are doing is that n is the total number of objects. So for each object what we are doing is that we are starting with a count is equal to 0. And then for every other object we are looking at the distance. If the distance is coming to be less than R, which is the threshold that we have set, we are increasing the count. And whenever we see that this count is exceeding this fraction threshold and the total number of objects, then we know that it is not an outlier. So then we are coming to, we are exiting this part of the loop and we are repeating with the next object. So finally we are going to get the list of all the objects for which we find them to be outliers. So here the interesting point is that since we think that the outliers are going to be very few, so most of the objects are going to meet the threshold, and not only they are going to meet the threshold, they are also going to meet the threshold very quickly. So in that sense, even though there are two loops of size n, so what is likely to happen is that instead of having a n square as the time complexity, it may turn out to be much smaller than n square. It may in fact turn out to be something of the order of n for executing this algorithm. But even when we have this algorithm where we are getting with a very good time complexity, There can be one challenge, that is, if we have a large data, which is likely to happen, then we are not going to be able to keep the entire data within the main memory. So what it means that we need to keep swapping the data between the main memory and the secondary memory. So that may be causing the that may slow down the algorithm. So and as we know, if we have a large data which is spread over a large region, there is no region that the neighborhood contributions, the neighbors will come from the entire data, but will only come from the data which is somewhere close to it. So if we can somehow divide the data and into, say, let's say few grids, and identify associate each object with a grid, with one of the regions in the grid, then it is possible that we will reduce the number of calculations significantly lower. So that is, instead of checking with the entire whole data set, we only check with the neighbors. And also we may take the advantage, instead of checking once we have divided the entire objects into the grids, so we have the groups of objects and we can compare group by group. So we have a grid based method for calculating for finding out the distance based outliers. So what we have done is we have divided the entire space into the grid. So in general, what we are seeing is a two-dimensional space, but if it's an n-dimensional space, so essentially we are going to get a multi-dimensional grid where each one of these elements is representing a hypercube with a diagonal length of r/2. Then we can prune the data for two reasons. One is that the point is not going to be an outlier, so we don't need to check further. So that happens when we have a possible point x in cell C and any possible point y such that distance is less than r. Then we can say that there is no need to proceed further because x can be pruned, and as a matter of fact, every object in the cell can be pruned. Then the other possibility is that, so for any point x in cell C, and there is any point such that the distance is r greater than r in level 2. So that is, we are looking at the cell C and we are seeing that we are first compared with the level 1 cells, and once we find something less than r, then we are clear that we don't need to consider this for an outlier. But here we are seeing that we are going into the level 2 cells and then the distance is coming to beyond r. Then again we don't need to consider this further because it's an outlier. So now we have pruned several objects, several cells, and so we are only need to check for the objects that cannot be pruned. And even for such an object which is not pruned, we only need to compute the distance with the objects in the level 2 cells, because beyond level 2 cells we are never going to get a neighbor. So in that sense, we have got a highly pruned data, and from there we have a limited set of calculations to detect the outliers. The distance based technique does have several limitations. First is that we need to specify the parameters r and pi, and we are going to get this percentage of objects which are going to be remote from the majority of the data. So the point is that we have a fixed value for r and a fixed value for pi. But the real world objects do not have such a uniform spread. So for that reason, the neighborhood definition itself cannot remain so fixed. So in such situations, the distance-based outliers techniques do not work. So now let's look at the density based outlier detection techniques. These techniques can give you some advantage with respect to the distance outliers. So here the point is that the density around an outlier object is going to be significantly lower than the distance density of the normal points. So we need to check the relative density of the object against its neighbors and see whether it is an outlier. So here we use the concept of a local outlier. So if we look at the objects, so O1 and O2 are close to the group of objects falling under C1. But if you look at, there are several objects which are densely close to each other. But if you compare O1 and O2, they have a distance from C1. Possibly they are representing a local outlier with respect to C1. But when you look at the other objects, so for example, which are forming a C2, another cluster, which has a lower density. So this point O4 is also away from C2, like if you compare with the distance of O1 with C1. But it may not be considered an outlier because the relative density of the points nearby. So this is somewhat like a dense urban area, and this you may take it as some village which is a sprawling village where people live way apart. So in that situation, any time when you see this much of distance in this dense area, this will become an interesting point. But in this case, there is such a spread will not be so interesting. So we define a term which is a local reachability distance, and that helps us determine if an object is an outlier. So first we define k distance of an object, which is the distance of the object with the kth nearest neighbor. And and we also determine the k neighborhood of an object as all the points O prime such that they are within the data domain and they are less than the kth nearest neighbor's distance. And as a matter of fact, NKO can be bigger than K because there may be several objects which are equidistant in different directions with the point of reference, which is O. So we can define another term, reachability distance of O prime to O, as the maximum of the kth distance of the object O, which is from the kth nearest neighbor, and the distance between the actual distance between O and O prime. So if this is higher than this, then only this will be considered. If it is lower than this, we are going to consider the distance with the kth nearest neighbor, so that we are going to get a smoother values, because sometimes there may be places where the density is so high that the reachability distance may become too small, and so the thing is, we are ensuring that the k is sufficiently large so that it can differentiate. And local reachability density is the way we define is that we are looking at the number of points within the k distance neighborhood for an object O, and then we are looking at the summation of the reachability distance of the object for each of the points within the k nearest neighborhood with the object of reference. So that is, we are trying to get an inverse of the average reachability distance. So that is, we are dividing it so that we are getting a density. So the way we define a local outlier factor is that we are dividing the reachability density of the reference point and essentially we are looking at all the neighborhood points, and we are divided by the reachability density of the reference point. So we are looking at all the neighborhood points which are coming within the k nearest neighborhood, and thereby if we are looking at the outlier factor. So if all the k objects within that are having almost the same level of density as the object of reference, then the outlier factor is going to come out to be small. It is going to be actually about 1 if it is same. But if it is going to be very small, then that means that this density is different, much different from this density. So if this density is for the object O turns out to be much smaller, then the local outlier factor is going to be much larger. So whenever you have a lower density, then you are having a reachability density of the k neighborhood. So then you're getting a higher LOF. So if you're looking at a object which is within a consistent cluster, then it is likely to be 1 for the local outlier factor for the objects wherever it is located within the cluster, because of the k neighborhood that we are considering. So whereby we are ensuring that it is smoothed out, and the object anywhere will be finding the k nearest neighborhood, and thereby we are going to get a smoother values. And we can also look at the significance of the local outlier factor by considering the distance, which is the direct distance, direct minimum distance. So here we are taking the k is equal to 3, the nearest neighborhood. So we are looking at, we have drawn the this circle, we using the third nearest neighbor, which is this point. So what we see is that the direct minimum distance is the minimum reachability distance for all the points within the k neighborhood, and then the maximum distance is the maximum distance of where they are all within the nearest neighborhood. So now let's say we also have the indirect minimum distance, so which is representing you are going into the neighborhood which are within the reachability distance of the O prime, where O prime belongs to the nearest neighborhood of the reference object, and then O double prime belongs to the nearest neighborhood of the O prime nearest neighborhood. Then we are again looking at the minimum and maximum reachability distance. Then we are going to get this relationship saying that local outlier factor is within these ratios. One is representing the direct minimum by indirect maximum, and the other one is representing direct maximum by indirect minimum. So in a way, it is representing the relative density of the object within the surroundings. So it is a good factor to consider when you are determining whether a object is going to be an outlier or not. So if we are coming to this example, so here what we see is that this is clearly an outlier, but in this case the O3 will be compared only with the density of the objects within the C2. So its 3 nearest neighbors, if we are looking at, are likely to be these 3 objects which are towards this edge. So it is going to compare the density, the local reachability density of the O3 with respect to those 3 objects. So thereby we are going to find that O3 is an outlier.